Thank you very much for this kind of opportunity. In this next moment, we would like to briefly describe our poster presentations entitled Elemental Analysis of Impurity Deposit on the Surface of Material using Metal-Supported Laser-Induced Plasma Spectroscopy. I'm Ali Khumaeni from Department of Physics, Diponegoro University. This research is collaboration research among Maju Makmur Mandiri Research Center, Kembangan, Jakarta, Department of Physics, Diponegoro University, and Department of Physics, University of Fukui, Japan. Our motivations is, it is known that in semiconductor industry, very low concentration trace metal impurity deposit on silicon wafer surface during manufacturing process. Uncontrolled contamination of trace metal impurities such as chromium can change the electrical characteristic. Therefore, high precision and high sensitivity trace metal elemental analysis is urgently needed in the semiconductor device manufacturing process. It is known that laser-induced breakdown spectroscopy has recently become a well-known technique for rapid and in situ qualitative and quantitative elemental analysis. In LIBS, a pulsed neodymium yak lasers is usually used as an ablation source. Experimentally, a pulsed laser or NDIAC laser beam was directly focused on a sample target to induce a luminous plume or luminous plasma. This plasma is then sent into the optical multi-channel analyzer via optical fiber to obtain emission spectrum. However, it should be mentioned here that LIBS cannot be employed easily to perform trace metal elemental analysis on a material surface, because when we focus a NDIAC laser beam on a material surface, the ablation of material itself will happen. Therefore, when we make a trace elemental analysis or impurity analysis on a material surface, the material itself will be damaged. In this present work, we suggest or we offer a new technique of LIBS utilizing pulsed CO2 laser using a vaporization technique. This is the setup of our technique of vaporization technique. The setup consists of two steps, namely new vaporization technique and acquisition technique. In vaporization technique, it should be mentioned here that two sheets of platinum metal mesh were tightly attached on a nickel metal plate. And then the mesh were then placed at 10 millimeter in front of the silicon wafer. This is a silicon wafer containing impurity or trace metal on its surface. And a pulsed CO2 laser was then directly bombarded on a silicon substrate or silicon wafer by defocusing a pulsed CO2 laser using zinc selenium lens. Why we should defocus a pulsed CO2 laser? Because we will not make ablation on a silicon substrate itself. We will only vaporize impurity or trace metal elements deposit on silicon substrate. By defocusing a plus 5 millimeter onto a silicon substrate, the impurity and trace metal elements vaporize and finally attach on a metal mesh or platinum metal mesh. In the second step, we make acquisition data by focusing a pulsed CO2 laser on a metal mesh and nickel metal plate to induce a luminous plasma. It should be mentioned here that in case of pulsed CO2 laser, when we focus a CO2 laser on a metal surface such as nickel and platinum metal mesh, no ablation happen by arranging the power density of a laser beam on a metal mesh. Therefore, when we focus a CO2 laser on mesh and nickel metal plate, completely no ablation of mesh and nickel metal happen. Only the plasma is induced from the surface, from the surrounding gas and surface of mesh. Therefore, by using this technique, we can make effective analysis by exciting and ionizing the impurity and also trace metal from the metal mesh after a vaporization technique. This is the plasma photograph taken when a pulse CO2 laser was directly bombarded on a surface of metal mesh and nickel metal. It can be seen that the plasma have a large diameter compared to Nd:YAG laser. In case of CO2 laser plasma, the laser diameter itself is around 10 millimeter or 1 centimeter, very big. This plasma has quite high temperature and also high electron density, and therefore the atom can effectively be atomized and excited in the plasma region. In these poster presentations, we only demonstrate chrome impurity or chrome trace elements deposit on a silicon wafer or silicon metal surface, silicon surface. The chrome itself contained at around 4 ppm level. It can be seen here that when we use our vaporization technique, we can easily get emission spectrum of chrome even at low concentration of 4 ppm. We can clearly detect 3 typical emission lines of chrome, including 4 to 5.4, 4 to 7.4, and 4 to 8.9 nanometers. This is the neutral chromium lines. Also, we should mention here that we can clearly detect hydrogen gamma 44.0 nanometer, which might come from the water or sugar during the sample preparation. After we obtain the good emission spectrum of chromium, we also examine the reproducibility of plasma by using our vaporization technique. It can be seen here that with various samples, we can get good stability of emission ratio between a chromium 4 to 5.4 nanometer and hydrogen gamma 44.0 nanometer, which means that by taking this data, we can conclude that our technique of vaporization technique can be used for semi-quantitative analysis of trace metal elements or impurity on a silicon surface. Also, it should be mentioned here that by using our vaporization technique, the silicon itself is never ablated because we use a vaporization technique by defocusing a CO2 laser beam 5 millimeter on a silicon surface. Finally, we make semiconductor analysis on chrome impurity or trace elements deposit on silicon wafer. The silicon wafer containing various concentration of chrome, namely 1, 2, 4, 8, and 12 ppm chrome ppm level. It can be seen here that we can successfully make a linear calibration curve of chrome, chrome with a ratio of hydrogen 44.0 nanometer with an intercept 0, which means that our technique of vaporization technique can be used for semi-quantitative analysis of impurity or trace elements on a silicon wafer surface. The detection limit of chrome was estimated around 100 ppb or part per billion level. Finally, as conclusions, a vaporization technique consisting of two-step process utilizing a pulse CO2 laser has been established and demonstrated. Good stability of the plasma emission was investigated. Using the present technique, a semi-quantitative analysis of chrome on a silicon wafer surface was successfully made. A good linear calibration curve of chrome using hydrogen emission line as a standardization with intercept 0 was demonstrated. The limit detection of chrome was approximately 100 ppb. And finally, the present techniques is potentially applied to analysis of impurity on material surface in material science and industry. Thank you very much for your kind attention.